Hello there and welcome back to this video series on control systems. So far we have seen a few preliminaries like system, control system and so on, and then went on to define what is meant by a Laplace transform, and we said this ft time domain function and capital Fs form a pair, and if we go from time domain to Laplace domain, we call it Laplace transform, and if we go in the reverse direction, that is from Laplace domain to time domain, we call it inverse Laplace transform. Further, we have seen some properties of Laplace transforms and inverse transforms as well. After watching this video, you will be able to specify what is a linear system, what is a time invariant system, and thus we say what is linear time invariant system, abbreviated as LTI, linear time invariant system. With that, we jump into this video and we try to define a system in a slightly different way as a black box. It takes an input, modifies it and gives an output. Okay, and very many times we represent this as an operator T with capital T, which takes an input, does some operation on it, modifies the signal x of t and gives it out as output y of t. Well, in general, the output y of t depends on time t, then initial condition, whatever is the condition at which the system is running, that initial condition, and also the input. But we represented here as though the system depends only on the input. That is fine for our purposes. Now, very strictly we have to say t acting on x of t at an initial condition x of 0 and starting at time t is equal to t0. But that's fine, we are keeping matters simple. This kind of representation is very handy, and we use this kind of representation to define what we mean by homogeneity in this next slide. When we say a system is homogeneous, we mean its output is proportional to input. If x is the input and y is the output, then if you give alpha x as the input, alpha y is the output. If such a thing is happening for a system, we call that system as a homogeneous system and say it's satisfying homogeneity principle. Mathematically, we can represent it like this. We are giving alpha xt to the operator t. So we put this alpha xt within the brackets. T acting on alpha xt produces alpha yt. Alpha yt is the output. A pictorial representation sometimes can be more meaningful, and in some other situations mathematical equation may be more meaningful. We'll look at both of them. Next, we go on to define what we call superposition principle. Let us say you have a system T onto which you apply an input x1 of t and you get an output y1. In another instance, let us say you apply an input x2 and you get an output y2. If alpha x1 and beta x2 both simultaneously act on the system as shown here, you take this x1 multiplied by alpha, take this x2 multiplied by beta, and you apply both these inputs onto the system where alpha and beta are constants. If the output is alpha y1 plus beta y2, the same combination of alpha and beta with x1 and x2, if you get the output alpha y1 plus beta y2, we call that system as satisfying superposition principle. Mathematically, we say that when x1 is the input, y1 is the output, x2 is the input and y2 is the output, when both alpha x1 and beta x2 simultaneously act onto the system, that is alpha x1 plus beta x2 is given as input to the system with operator t, then if the output is the same combination, you see here alpha x1 plus beta x2, Here you see alpha y1 plus beta y2. If such a thing is happening, we say that the system is satisfying superposition system. If a system satisfies both homogeneity and superposition principle, then we call it a linear system. In general, we notice that real life systems are all non-linear. They are not linear. But in a small region of their operation, they may be approximated as linear systems. And thus we study linear time invariant system. And we see what is this time invariance in a little while. Let us say you have a system T as shown here. It takes an input x of t, modifies it according to whatever is its internal arrangement, and gives out an output y of t. To this system, let us say we apply an input x of t. Whatever is the time dependent shape of this x of t, we give it as input, and let us say we get an output as shown here, whatever shape it is. This input and output relation depends on the system that we consider. Now to the same system T, let us say we apply an input as shown here, that is exactly the same shape but delayed by a time interval tau. The delay we represent as t minus tau. Okay, as you go along, you get used to the notation. Okay, if the output is a delayed version of this original output, then we say the system is time invariant system. That is, if a delayed input gives the same output delayed by the same interval tau, then we call the system to be time invariant. We'll try to say it mathematically because that comes in handy at times. We will say that a operator q tau is defined that delays its input by a period of tau. You can see this operator q tau takes in an input x of t and gives out a shape which is exactly the same but delayed by a time interval tau. Okay, then we say that a system is time invariant if it satisfies this equation. That is, you take input, delay it by tau, give it to the system and see what is the output. If that output is exactly same as the output you take here with the undelayed system and delayed by tau, if both these are identical, then we say the system is time invariant. You may note the brevity and beauty of mathematics. All these pictures and description above is defined in one equation. That's the reason why we try to look at mathematics on and off. In fact, if the entire subject on control systems is full of mathematics. The abbreviation LTI stands for linear time invariant. So a system is, if it is both linear and time invariant, we abbreviate it as LTI. The output-input relation of an LTI system is represented by a linear differential equation with constant coefficients. These are the differential equations that you have already seen in your mathematics, first year mathematics course. With that, we may summarize this video as a linear system obeys the principle of homogeneity and superposition. In addition, if it is also time invariant, that is, if a delayed input to the system gives the same delayed output, the system is termed time invariant. Okay, LTI systems are both linear and time invariant. Okay, the input-output relation of an LTI system is linear differential equation with constant coefficient. I think that's all we have for now. Have a great day.